type inference, code compression, and more. So what I thought I did, since there's a whole bunch of programming language and compiler nuts in this audience, I'd go talk a little bit about stuff I've done in the area of programming language design and implementation in the past. So I'm going to give a brief overview of the more significant projects I've done there, and then I'm going to do a slightly deeper dive on two topics within two recent projects that I think you might find interesting. One is about, call it code compression, but really it's about whole program refactoring. And it's one of my crazier projects I've done. And then a more traditional topic, which is about flow-sensitive type inference using specialization. And yes, as it says, please feel free to interrupt me at any time with questions rather than waiting until the end, whatever you prefer. Okay, so let's first start with my enormously long list of programming language stuff I've done. So first larger compiler project I worked on was called Amiga E on the Amiga platform. The language itself was not particularly remarkable. It was just a mishmash of procedural object-oriented functional features that mostly had a C, C++ style semantics and a bit of a Pascal-like syntax. What was probably more interesting was that its implementation was entirely in assembly language, which was really crazy. At the time, I was doing a lot of graphical demo programming in assembly and was very comfortable with it. So when it came time to write a compiler, I thought it was a smart idea, which it wasn't in the end. But I did it anyway. It did have some good consequences though, because it ended up, even though it was a large and complex language with a lot of functionality, it ended up being a very, very small and fast compiler that generated pretty decent code. And that made it very popular, because the Amiga platform at the time, most people still didn't have hard drives or things like that. So like a small language that you could have on a floppy disk and still generated like C, C++ style code quality was very popular. It was pretty full featured in terms of APIs and came with a graphical debugger and editor integration, a whole bunch of stuff. And it quickly became one of the more popular languages on the platform. I even sold the compiler for it for a while, which made me enough money to pay for my PhDs, and it was good times. And at its high point, I was even an invited speaker at a conference alongside Richard Stallman for this particular project. So it was all downhill from there, clearly.
Did Richard Stallman work on this too, or was he in
No. It was just merely coincidence. It was a conference about alternative languages and systems, and I was there as a language author, and he was there as talking about free software and things like that. Second project is a much smaller project, but was still somewhat significant. This was my attempt at making esoteric programming languages, a stack language that have very obscure syntax. My main goal was to write as small as possible compiler for it. So I wrote a compiler, again, in assembly language, because this time it was actually necessary. And the compiler executable ended up being less than 1,024 bytes, implementing a programming language that had like function calls, variables, loops, conditionals, and a whole bunch of built-in functionality. Which, funnily enough, it would generate directly 68K executables, most of which were often much larger than the compiler itself, so that was kind of funny. So like I said, fairly complete programming language. People would actually write like games, and someone wrote a virus checker in it. There's a little example there of what it looks like to compute the first 100 prime numbers. As you can see, it's suitably unreadable. As you can imagine, from a stack language where every operation is a single symbol. Most interestingly about this language is that it kind of spawned like a whole wave of esoteric languages back then. Most famous is a language called Brainfuck, which was written by someone in reaction to this language. They said it's like 1,024 bytes, that's way too big. I'm going to write one in 256 bytes. And that's how Brainfuck got started, and there's other languages like bfunge. So yeah.
Is it accidental that the brackets match on there?
No, that's actually the only syntactic feature that the compiler checks.
Okay.
The square brackets are actually like a function definition, like an anonymous function. So, and that makes the language much simpler, because the question mark, for example, is an if-then, and the hash mark is a while, and those just take like closures on the stack basically.
Okay.
So that's why that's all pretty simple. The next one is the one I made for my master's thesis, and it was about extending functional programming with first-class environments. So the one special feature about that was that I merged the concept of function definitions and class definitions. They were both the same. And if you want the class, then basically you could access the stack frame of the function as it being an object. So basically there's a special value called self inside every function that if you pass it along somewhere or return it from the function, then you would essentially create an object. Therefore, classes and functions became the same thing. In hindsight, not that special other than making the language like a bit simpler, but it was a fun project. Allow you to do cool stuff like on-the-fly anonymous objects. So the function you're in can actually be an argument to the function you're calling. If the function you're calling needed like a callback with particular methods or something like that. So a lot of crazy stuff like that. Also had nice Hindley-Milner type inference, generosity, pattern matching, exceptions, fairly complete language. And you see a small example there at the bottom of how you would define like a stack, for example. It shows off the generosity and the self is, this is actually, the stack is actually a function in this case. It's not a class definition. All right, let's keep on tracking. Then for my PhD, I did a language called RDAPO, concurrent tree space transformation. So what that means is a combination of a tree or term rewriting programming language, which is purely functional, and I combined that with what you call a coordination language, so a language for doing concurrency based on tuple spaces. And the idea was that the tuple space would not only take care of concurrency, it would also take care of storing the state. So the tree rewriting could be purely functional, and the state would be separate from that. And that would be a pretty cool way to kind of mix like the functional and imperative paradigms. Also, it has completely graphical syntax that was based on programming by example. I'll show you in a second what it looks like. And it was implemented in Java, which was not the greatest choice, but at the time it seemed like a good idea. The cool things about that was it had a very simple graphical editor, and it could compile the bytecode like right inside the running program, which is pretty cool. Oh, and it had a distributed runtime, so you can run it across multiple. Your computation could run across multiple machines quite easily, which is kind of a feature of like having a tuple space-based model. Of course, you're wondering what that looks like, so I have a screenshot here if you all can see it. That's going to be hard to see for some. So I guess what's interesting to point out, so between the big black bars, you'll see that there's basically one rule that rewrites one kind of expression and another kind of expression. The interesting thing is the programming by example. So that means that rather than having variables or placeholders, you actually have actual values that are meant to indicate. So in this case, for example, if you look at the code on the left, that implements quicksort. So you'll see the second rule, rather than saying like, I'm going to take the head and the tail of a list, or rather the pivot and the rest of the list, it actually has an example list there, if your eyes can spot it, that starts with 5 and then a bunch of other numbers. The 5 is the pivot and gets used as the example pivot rather than the word pivot. I'm not sure that makes sense, but they don't want to dwell on this particular language too much. But anyway, crazy project. 2 more languages that I made for 2 different companies. The more interesting thing about these languages is they both have an alternative memory management system, kind of like Rust. So they both have like some kind of like unique ownership model. So the first one in particular is based on uniqueness typing or linear logic. The big difference with something like Rust is that where Rust gives you an error if you try to borrow something that you're not supposed to borrow, this language is actually just make copies of values if things couldn't be kept unique, which of course is potentially inefficient, but it was also meant to be a lot friendlier. And there used to be ways of finding out where you're having copying and stuff like that. So unlike Rust, it would not look like, you would not be confronted with like a complicated type system, basically.
Can you statically tell where you're inserting a copy?
Yes, yeah. So the idea was that you would have a profiler that would say like, if for the performance was not to your expectation, to tell you like top 10 places where you were generating copies or something like that, if you were interested in that kind of thing. It also had, so generally was strongly typed, had multi-methods, pattern matching, and it compiled to what I consider the predecessor of WebAssembly, Tao's VP virtual processor technology. They had way back when. And then CryScript, another language that had a slightly different ownership-based memory management that was based on regions. So you would reclaim regions all at once. So a bit more efficient. We're getting to more recent projects. So this is a crazy one. I'm going to go into more of it in a little bit. It's called Restructure. So automatic whole program refactoring, what that means is it will take a whole code base, not just a part of it, and it will find things to abstract into functions and to inline until the code has no more redundancy anymore, meaning there's no more repeating copy-paste code, and there's also no more unnecessary functions. That sounds crazy, it probably is. This was motivated by my observations of seeing, actually I was teaching at that time, so that's probably what motivated that. I was seeing that making programmers responsible for factoring out their own code by fixing under abstraction and over abstraction is a lot of work, and it really is a compression problem. So computers are good compressing, so I thought, like, well, let's see how far we can get making computers responsible for this and allowing programmers just to copy paste away and not having to worry about like what kind of functions this would result. So I implement this as a prototype. It's again a graphical program editor, and that has reasons. With .NET code generation, that was convenient at the time. There are problems with it. As you can imagine, the big problem is that it reorganizes code too much, so programmer lose track of like where their functions are and things like that. But it's still very interesting, and I'm going to do a little bit more detail on this particular design in a bit as one of the things to continue on. Then the last one, this is my most recent programming language project. It's a language, this time I made specifically to target games. It has a syntax that if you squint looks a little bit like Python, but it is has a more regular syntax with extremely lightweight function values that are meant to give any higher order function in the language the same kind of syntax as built-in control structures. Also important, besides the syntax, we also have the same semantics as built-in control structures. For example, most programming languages, you can make a higher order function, but then you can't return from that higher order from the lambda inside the higher order function, which means you can't really use it as a control structure because control structures that you can't return from or can't escape from are a little bit pointless. So this language, for example, allows that. And generally it was meant to make refactoring code using higher order functions very easy, because that's kind of like how I tend to program. Using objects, I tend to use higher order functions to structure code a lot more than most people. So the big difference with something like Python is it's very strongly typed, but its purpose was to make code feeling like you're in a dynamically typed language by not burdening you with like a lot of type annotations. And that's where that new type inference algorithm comes in, and I'll talk about more in a second. Beyond that, it had multi-methods, coroutines, built-in vector operations, immutable objects. It is statically nil-safe, and it also has some simple functional reactive programming style cross-frame variables, which I won't go into. It can run on either VM or compiled C++, and of course comes with a built-in game engine. All right, so that was my list of most significant projects that I've done. So now I want to go into two topics and talk a little bit more about those in detail. So the first one is the code compression we just mentioned for the Restructure project, and let's see how that works. So at its core, if you talk about code compression, the concept is pretty simple. You just find repeating code, introduce functions for them, and whenever possible, you inline functions that are only used once. That's the absolute basics of it. The actual algorithm is still somewhat complicated. It took me a while to figure out it anyway. There's a couple of things which are difficult about it. The primary thing that you really need to think about in terms of design is how to deal with side effects. If you abstract things into function arguments, you change their location, which means that you may be changing the order and, more importantly, the amount of repetition of particular side effects, which of course you can't do with side effects to retain their meaning. So you have to have some kind of facilities for that. Talk more about that in a second. You need to design good heuristics, because the amount of possible refactorings that you can do are endless, and they often overlap. So you need to choose like which one is the better abstraction out of two. And then of course you also need to be efficient, because the naive version of the algorithm is just match every possible ASD subtree against every other possible ASD subtree, and then repeat that like thousands of times until you're done refactoring. So the naive version is very, very slow, so that somehow needs to be made faster. So here's a first simple example. So if you look at the expression up top, it has some clear similarities. So there's at the beyond the root level, there's the two pluses that are similar. And there's not only are the minuses are similar, but both the number before the minus is also similar. So if you let the algorithm run on this, you end up with the code at the bottom. So what you'll see there is, like at the root, it has the SB, which encodes what happens on two sides of the multiply. Then B is implemented this term as the plus of the two sides. And then A implements the minus expression. The one kind of confusing thing about this is that the A function is actually a function that's local to B. So it uses capital A as a free variable, if you will. So it's not an argument to A. Again, if that is not obvious to you, then please ignore that. I'm just saying this is a very simple example that shows like it will take code and find repeating patterns in it and turn those into functions. I'll have a larger example of that later on. I don't think I actually have a very realistic example here.
So the bracket A on the bottom, that's sort of like saying it's like a capture clause?
Yeah, it's just kind of annotating that this function has this uses capital A as a free variable.
Okay.
Basically, that's just how I happen to have annotated this at that particular time. Yeah. But my thought was, like, it's nice to have functions that are local to other functions, because cognitively that means you have less functions to look at and less to understand like how to relate to the rest of the code. So that's why I wanted to make local functions as opposed to keep all the functions at the global level. Okay, so let's talk about side effects. Why are they difficult? So like I said, it may change the meaning of an expression if you move them. The simplest solution for side effects is, of course, to just wrap every side effect in a closure, and that way you control when it's evaluated. But most programming languages, closures are relatively heavyweight things. So if you start doing that, most people in most traditional programming languages start seeing like lambdas all over the place for their assignments. They're going to freak out a little bit. So that's probably not a great solution. So two things: you probably want a language where closures are relatively lightweight things syntactically and semantically for this to work. And then second, also important, one thing I am doing in this prototype is to perform an analysis that whenever possible, that the order of side effects does not change, that you omit the closure. So try to produce as few closures as possible. But what you also should do is just favor refactoring that do not require a closure to be introduced. Of course, you could say, it's like, hey, why build this problem at all? Just do this algorithm on a purely functional language, but I consider it almost cheating because that would make this algorithm way too simple.
Why do you need to use a closure as opposed to a local variable that you send?
Well, this is assuming that the expression contains a side effect gets moved outside of the function. So if you have a function where...
Oh, then you're passing in the closure instead of the computed value.
Yeah.
Okay.
So imagine if you, for example, have maybe you have a for loop. And the for loop is a repeating part. And what's in the body of the for loop is the unique part, needs to become an argument. So yeah, so here's a side effecting example. this weird syntax that you're reading there at the beginning says like, it's kind of like let syntax. It says like let x equals 2 in this expression. And inside the expression there's 2 assignments. It's an extremely contrived example, so try to ignore that you would not ever write this kind of code.
Do you specify an evaluation order?
Yeah, this would have a very deterministic evaluation order. It's not like C or something like that. So yeah, assume it says like just a left to right evaluation order or something like that. So what's happening is here the code is finding out that basically that X has a side effect dependency. So what it does, it moves it out into a separate function to guarantee its evaluation is being delayed till later. And again, it does not produce the simplest or the most elegant code. And also, this syntax is still, it was meant for that to be in line syntactically, which is not the case here. So this looks a little bit clumsier than it should be, but anyways, to show that the algorithm knows how to find side effect dependencies. Now let's talk about efficiency and heuristics. So the core is pretty simple. We take all refactoring opportunities and we sort them by the number of occurrences. So the big heuristic is assuming that like if something occurs more often, it should be more likely to be moved into a function than other possible opportunities. And the way it works is that once you apply a refactoring, you probably are invalidating other opportunities for refactoring. So once you go, they need to be invalidated as you go down the list, basically. The way this is kept simple, because the question is like, well, how big of a subtree are you trying to produce into a function? The way I've solved that is to only refactor a very, very small subtree at a time, namely the root of a subtree plus one of its children and not the children beneath there. So it's a super, super small little function. Of course, you would think like, you're generating a lot of like small functions with that are useless. But this gets combined with the inlining to produce bigger functions again. So it basically produces a ton of really, really, really small functions and then inlines to get bigger functions like out of those. But by doing it, by restricting it to something that just touches 2 nodes at a time, the algorithm is kept relatively simple. What else? So yeah, this does make it slightly less efficient and generates enormous amounts of objects that could probably be done better.
So is there a way to like sort of outline things once they've been inlined? So if you ran the algorithm and then you change something and run it again, would it like be able to refactor?
Yeah, it does that all the time. So yes, things drop to be when they're being inlined when it's just one use case. But then when you take a code, maybe the programmer copy pastes it and puts it somewhere else. Now suddenly there's 2 uses, and that code gets made into a function again. Or more subtly, sometimes there's like 2 possible. There's like overlapping. Like you have a longer stretch of code, and then in 2 other places there's 2 overlapping uses of those, and you pick the one that is the longest or the biggest match. But then the code changes maybe, and then the other option now becomes the longer, biggest match. And that gets put into a code. So your code can change around pretty drastically with this, but it will always find the most optimal factoring of function this way. I haven't proven that, but that's my claim. I'm not a very formal person, if you hadn't noticed.
That's an interesting question, whether it would always converge on the same stable result.
Yes, again, I'm not proving that either, but I'm pretty sure that it's a converging algorithm, yes. It's pretty deterministic in how it executes. So algorithm outline, I already told you guys most of this. So repeatedly, it's going to find like all possible combinations of 2 nodes, count the occurrences of them, sort them by number of occurrences, then create small functions for each of those, assuming they haven't been invalidated by an earlier occurrence, and do some other optimizations, like, for example, existing placeholders can be promoted to free variables, Arguments that are equal can now be reduced, so you can reduce the number of arguments of functions. And of course, like I said before, it's going to check for the side effect rule to see if we can avoid creating closures. And then at the end, it's going to do a pass of just inlining everything. It just has one caller. So it does this repeatedly. Here's a crazy example. So I made this just kind of to test the algorithm. I just keep on copy pasting subparts. Look at this as a human. If this were real code and you were asked to refactor this, this would probably be an extremely painful exercise for you to do. It would probably take you hours and hours and hours and you probably wouldn't be confident that you had refactored it in a way where there's no more repeating expressions. But of course, the algorithm doesn't care and just goes and does it. And then you get this crazy code out of it, which probably, again, is not super readable for some people. The only takeaway, well, first of all, this code doesn't look like a lot more readable than the previous code, but it is kind of magic in the sense that instantly it is able to find like a set of functions that guaranteed have no common sub-expression repetition anymore, and finds the, whatever is the simplest factoring of all those possible functions.
So at least in that one, you could also just, it looks like replace it with a number. Do you do any like partial evaluation too?
Sorry?
Do you do any like partial evaluation or like, because all I saw there were like numbers and operators, and so it looked like you could actually just like fold all that into
This does no optimization or of any kind. It would be separate.
Okay.
Yeah, I guess for the purpose of example, you kind of have to assume that instead of integer literals are variables.
Yeah.
Right? So
And it's also, because this works, and this is a software engineering tool that's meant to work with the programmer.
Mm-hmm.
If the programmer explicitly has like 2 times 3 in their code, that's probably because they actually want to write it that way. You don't want to make it into 6 because you might actually be kind of destroying the programmer's code. So optimization would be like after this, basically. All right, so that was the restructure project. So now something a little bit more mundane, but still very interesting, I think, is how I recently implemented this type inferencing algorithm. I guess a little bit of context. This language was originally dynamically typed. And then at some point I decided, I think I can actually make a type system that is going to not be in your way and not be painful. And that's how I designed this type system. So probably the biggest feature about this type system is that it uses specialization as opposed to trying to infer generics. If you look at like how Hindley-Milner works on like Haskell or something like that, the whole point is to infer generics, but it requires more complicated features to be powerful, like type classes and whatnot. This one works more like C++, if you will. If you imagine taking all your functions in your C++ code base and all just prefixing them blindly with like template declarations, so that every function works on anything that can be type checked, then you almost can get this system. Except this system, of course, is a lot simpler than C++, so it doesn't generate the crazy type errors that C++ would do. So the simplest case, it basically type checks. It type checks one instance of a function for each permutation of the argument types. So that sounds like there would be a lot of code duplication. In practice, it's not actually that bad. I mean, of course, C++ deals with this too. I've measured it, and so far at most there's been like a 2x blow up of code. The cool thing is, because you're duplicating some code, that gives the optimizer more to work with. All code is specific to particular argument types, can be inlined more readily. So it actually, efficiency-wise, it's great. It makes for a simpler type checker, but it's at the same time more powerful than what generics can offer you. Because generics, there's always a limit to like what kind of generics you can infer, whereas this can deal with like any combination of types at any time. So that's kind of the main secret behind this. The other big thing is that typing is what I call flow sensitive. So it means that type inference works in the order of the call graph. And that means that the type checker generally has maximum information because it knows the context where something is being called in. And the this language has a lot of free variables and, again, like I said, higher order functions, which kind of require this level of information to be able to type check those kind of complex constructs without requiring you to actually write type annotations. So,
have you looked at any of the type bracket work?
Sorry?
Have you looked in the type bracket at all?
Type bracket. At some point.
Or I think there's typed closure also, which is pretty similar to it.
Okay. No, not in detail. I don't think.
I feel like they have some ideas that are similar to that, like the, you take dynamic code that's got if this is a string, then do this, and so in that branch you can assume it's a string, and the other branch it's not a string. And so it's kind of cool to see similar ideas popping up in context.
And that's actually very appropriate, because if you start from like a dynamically typed language, in this case I already had like a lot of code written that was written assuming that it was running on a dynamically typed system. And I basically want to be able to type check that code, but do as little damage to it as possible in terms of type annotations.
Yeah. And
then you have to invent a system like this that really basically is very liberal in what it allows.
I was reading a retrospective on Erlang by Joe Armstrong, I think, and he was talking about, he's like, oh, and then one day like Phil Wadler came along and decided Erlang needed a type system, and so it was actually surprisingly easy to add it, because it's like, well-tested programs tend to be well-typed, even if you haven't explicitly written down like what the type system is.
Oh yeah, I found the same. There was hardly any occurrences that the code didn't fit the type system, basically. Yeah. So, so like I said, because of specialization, you only work with concrete types in the algorithm. There's no generic parameters or anything like that. It uses conditionals and general Boolean logic and asserts and all those kind of things to make types more specific than what were declared or inferred initially. So that means that code inside if and else blocks can make more assumptions, basically. And the cool thing is like that before it was a type error, you get a stack trace at runtime, and now you get a stack trace at compile time. Because when a type error is generated, it knows the location where you are in the code. I can give you context in terms of like where these values were generated that are causing these type errors. So let's look at the simplest possible example. So here you have a function that just adds two things, and as you can see, it does not specify any types, of course. You can then call it with like different kinds of arguments. And you see an example where they're being called with sets of arguments that are clearly very incompatible with each other. Other languages that would want to type check something like this with generics, they would need type classes or something similar for the template parameters, just to be able to express like, hey, these things need to be able to support a plus operator. In this case, none of that complexity is required. Of course, there's no dynamic overhead. You just get two copies of this function, and it generally gives you the style that you can write code pretending that you're in Python, but you still get the benefit of like static typing behind the scenes. Slightly more interesting, like stuff like compile time conditionals that can type things that generally not possible in other languages. So here you see a function that if we call it with a string, for example, most languages would give a type error because you can't divide a number by a string, for example, because it typically type checks the entire code, regardless of whether it's executed or not. So in this case, it statically omits one of the two branches, and therefore this can type check correctly and give a particular return type. C++, for example, was not able to do this until recently. Recently gained the if const expr that now allows you to do similar stuff to this, which is extremely useful when you're making more complex templates. But I'm saying in this language, that kind of comes naturally and still gives you strong typing in these kind of complex cases. And finally, an example, like I said, we have statically typed nil. So this language will never ever give you a null pointer exception, even though nil is part of the language. So an example of how that works. So here you first have a variable that's assigned to nil. So we don't even know what kind of nil this is. So it's a nil of an unknown type, or a type variable, if you will. Then conditionally we assign to this variable. Now we know at least its type, so we know it's a nillable string, which is annotated with like the question mark, which you've probably seen in other languages. But so it's still possibly a nil value. So the next line, you cannot now do something with that value because it might be nil. It doesn't allow you to. What you can do is you can of course use a conditional, like if a, and now inside the block, this is the flow sensitive part of it. Inside the block, A has a type string as opposed to a nillable string. So it's temporary. As you exit the block, it becomes a nillable string again, basically. So now you can work with it. And like I said, it also works with assert and other things. So yeah, that's pretty nice. And there's another feature where I've noticed that, like, if you have well-written code, you typically are already checking. So it's not like your code becomes more complicated, but you just have better guarantees that certain things won't happen at runtime.
Is there a way for the programmer to sort of make their own sort of annotations to the type system to tell it that sort of thing? It's like a certain if built in, or can you implement it inside Lobster?
Can you think of an example for that? Because you're trying to say, because these things basically guarantee that, you know, something can't be the case for this particular type.
What I mean is that what you're sort of describing is converting from one type to another type based on some operation in a way. Like assert is maybe a better example because it's just like you do this thing and now it suddenly becomes a new type, right?
Yeah.
So maybe that's all you need, but I'm wondering if there's an example of where like you've wanted to do that from outside of the compiler, you know, like in user code, or is that just not necessary?
No, there probably is. I can definitely tell you this language currently, it's all hard coded to certain language features to help you with that. I can imagine like values being in a particular kind of range or something like that. That's something the type checker could track, and then you don't have to test for it anymore. There's probably examples of that, yeah.
It seems like this is like the type checker has to know that there's certain functions that have like implications for the type sense, or for like, you know, yeah, for the type system. So like, you know, the is this a string function, like, you know, that tells you something about whether it's a string or not. But like if I just wrote my own, like, you know, is this a prime number function, for example, like it seems like the language may not understand like, oh, prime number is now this new concept that I can track.
That's a good point. Yeah, unless you also made it like an error for that to be prime numbers or non-prime numbers to be passed to certain constructs, then this analysis would not be necessary, I guess. But yeah, you're getting into the area of dependent typing, I guess. Those languages would be able to express this stuff for sure, but this is relatively simple language compared to that.
I think early versions of Rust had type state, or at least there was an intern who tried to make it have type state. It was fun to have it, and the idea was that there was like a pure subset of the language, and then you could use that to write like assertions, and then the type state checker would make sure that, like, you know, you could say like, oh, this function needs to pass, or like this value into this function needs to pass through this assertion first, and then like there's a flow sensitive analysis that would make sure that that's the case. But I think it was just sort of too complicated to make it work, so they pulled it out.
That's good to know. I won't attempt again. Okay, well, that's all I have for that topic. So if you ever wanted to check any of these things I mentioned again, you can find them linked from my homepage. And if anyone has any remaining questions.
You actually got that address?
How much have people offered you to buy that domain?
Not really.
Oh.
I got this relatively early on. It's like, let's get a fun programmer-related domain, and I just started putting function names, and this is the one I found was still available. But I guess, like, for most commercial purposes, this is like most people don't even, like, there's plenty of programmers don't even know what this means. So, let alone other people. I don't think it's that valuable.
Maybe programmers wouldn't.
But I like it. I've had it for a while, so.
Yeah, that's awesome.
How much of this sort of adaptive static typing could you use in a compiler for an existing language as an optimization feature?
I totally think you can, and I believe there are examples out there. There's probably some Python implementations that do something like this. But of course, the problem is if you can't really enforce it in the language, actually TypeScript to some extent uses a lot of techniques that are very similar to.
It would give you very different benefits. It would not give you static type checking, especially in an environment like JavaScript where you typically don't have whole program views, so you can't enumerate all the callers of a function.
Yeah.
But it might potentially give you performance benefits if
For code it
if you
can
can
be
dynamically
analyzed.
do this inside the optimizer compiler when you inline stuff or
Isn't this the same sort of thing that Turbofan did for ASM.js ultimately?
did it? I don't know.
My understanding is that like before a lot of the work to add specific parser for ASM.js, you would have integer ranges that you could basically, or like type classes that you could track, and that was done by basically saying, oh, whenever you do an or 0, this is what it means now, that kind of thing.
I guess you could call that a very simple form of it. Yeah.
Right.
It gets more interesting when you get to the area of letting the compiler decide to duplicate certain fibers of control flow, maybe within a function or maybe across inlining boundaries. So polymorphism polymorphism could be an example that leads to that, or the interplay between branching and dynamically generated type checks.
Yeah, that's definitely more advanced than the stuff that I saw, at least in ASM.js code.
ASM.js doesn't really need much of it because ASM.js is strongly typed. It uses weird syntax to express that, but it is effectively typed code.
Yeah, it's explicitly typed.
Yes.
So there's need much type inference.
So this would be more interesting for plain old JavaScript, where you could have a string and a number showing up in your addition, and doing the dynamic dispatch for every operation can be relatively expensive.
I mean, I think ASM.js though is sort of a realization, like that's kind of taking this idea of like, oh, what if we could infer something about the types just from the syntax, and like taking it to its limit, which is, like because it's a strict subset of JavaScript, it's the or 0 thing, it just like as a side effect coerced whatever you put it to into an integer, and so they said, oh, we'll just call that a type annotation now.
The key technique here, or one of the key techniques, is to dynamically duplicate code and sort of instantiate 2 different template versions of it.
Yeah.
ASM.js doesn't need that. It'll always only be one.
Right.
It can infer things about that one, but it never needs to dynamically duplicate.
Right. Did like TraceMonkey or any of the early trace-based JIT compilers, did they do any of that?
Work on those.
Because I can imagine it's like, oh, this time we ran this with an array of strings, and this other time we ran it with an array of events.
In V8, we toyed with the idea, mostly if we had patterns of one polymorphic dispatch and then a few common things, and then the next polymorphic dispatch, to just have fewer of these diamond schemes by combining them into one large diamond and then duplicating the middle part.
Right.
I don't think we ever implemented
Never
it.
did it. That was one of the big promises in Turbofan. Not because of side effects, it just turned out to be hard enough that it wasn't the thing that was the problem that we had to solve next.
I guess you could argue that C++ has like kind of a pathological version of these like type things, in that like if you assign to a pointer, it takes that as an assertion that the pointer is not null, and then is free to eliminate any null checks after that.
Yeah. But yeah, it doesn't help the programmer with it.
Right.
Yeah.
And then we say that references are supposed to never be null, but then sometimes they are.
Yep.
So, yeah. Anyway, anyone any more questions or comments?
What would you say is the largest program that, I think I've asked you this before, but in Lobster, that people have written? Or you?
Oh, I've written a whole ton of game prototypes in it, and some of them are pretty large. I'm not sure in terms of lines of code, a couple of thousand maybe, I don't know.
Yeah.
I mean, the language is such that, like, at least for my coding style, it keeps code extremely short and simple. So lines of code probably not the best measure. But yeah, the total amount of code that's been written in it is substantial at this point. Cool.
What's your next programming language?
Good question. Actually, working on, of course, a ton of potential things. Not sure which one is the most fruitful. One fun thing I'm currently working on is a programming language that does not have any dynamic allocation whatsoever. And I'm not going to explain to you how it achieves that, but I think I have an interesting idea.
That sounds awesome.
Yes, and it will be very, very suitable for WASM. So
It will be very what, sorry?
suitable for WASM.
Uh-huh.
Well, that's just one, but as you've seen from some of the things I worked on, like memory management, definitely a recurring theme in what I work on. Very obsessed with making things efficient and fitting caches and stuff like that. So this is one more of such a project. I guess I go back and forth in terms of what I'm interested in. Like when I started this last project, I thought, like, let's do dynamically typed languages again because they're simple and fun. And then while I was doing it, I discovered, like, no, I don't like this. I want stuff to be fast and static. So I'm not going to swing back in the other direction. So what else am I working on?
I guess that means after the no allocations language, you're going to implement the GC.
Yeah, maybe because I decided that, like, it's not worth the yes. Yeah, that's kind of how that works. So, and I keep doing it and then I die. So it'll be good.
How about new table gen? It's terrible.
I can totally make a new table gen. I think I understand how it works now. So
Okay, that makes one of us.
yes. Yes, I have a long list of things that are potentially cool but are pretty vague at this point, as they always are. All right, no more questions. Thank you for listening.
Wait, I have an administrative question. Do we have anything planned for the next tea and crumpets? Do you know, Eric?
I don't think we do.
Okay.
Good from memory. So yeah, if anyone wants to give a talk, you should sign up.
All right, cool.
Anyone wants cake?
Cool.
Thank you, by the way, yes.